All right, for number 10, I'm going to do a little bit of a shortcut on the basis of what was just done in problem number 9. Okay, problem number 9, we had attained the inverse Laplace transform of 3 over s squared times the quantity of s minus 6. And in the case of number 10, we had the Laplace transform to be 3 over s cubed times the quantity of s minus 6. And for f of t, we're looking at the inverse Laplace transform of this ratio. And if I rewrite in terms of integrating, I can take the original Laplace transform, multiply by s directly. And so that's going to cause s cubed to go down by a degree to s squared. And moments ago, we determined the inverse Laplace transform of 3 over s squared times the quantity of s minus 6. And putting this inverse Laplace transform set up into the integral. So for 3 over s cubed times the quantity of s minus 6, we can say that's going to be equal to the integral as tau goes from 0 to t of what is going to be, in this case, negative 1/12 minus 1/2 of tau plus 1/12 of e to the 6th tau. And again, with the letter t, this would and was the inverse Laplace transform of 3 over s squared times the quantity of s minus 6, except we have now in the arrangement we have t in terms of the variable tau. And now looking at the integral, attaining the antiderivatives, so we're going to have negative 1/12 of tau, and we have what's going to be minus 1/2 times tau squared over 2, so this will be minus 1/4 of tau squared. And we're going to have for the last term, we have 1/12 of 1/6 of e to the 6th tau. So we have 1 over 72 times e to the 6th tau as tau goes from 0 to t. And so with tau set to t, I have negative 1/12 of t minus 1/4 of t squared plus 1 over 72 times e to the 6th t. And with t at 0, okay, the first two terms are negligible. And we'll end up with the last term transformed to minus 1 over 72. So we have these 4 items in the final result for problem number 10. All right, for number 11, okay, we have f of s is equal to 3s minus 4 all over s cubed minus s squared minus 6s. And if I factor out the letter s, the greatest common factor, I have 3s minus 4 all over s, and then factoring the second order trinomial, we have the quantity of s minus 3, and this will be times the quantity of s plus 2. Okay, for number 11, okay, we have the inverse Laplace transform set equal to 3s minus 4 all over s cubed minus s squared minus 6s. And factoring the denominator, greatest common factor is going to be s, and this will be s times the quantity of s squared minus s minus 6. And factoring completely, we have s minus 3, and s plus 2 in the denominator. And taking the inverse Laplace transform of what we have in the ratio, and what I decided to do was rewrite this in terms of integrating, and that'd be so as to get rid of the s. So if I multiply this ratio by s goes out. So we're looking at in line with integrating. I'm looking for the inverse Laplace transform of 3s minus 4 all over the quantity of s minus 3 times that of s plus 2, and taking the partial fraction decomposition of this adjusted ratio. Okay, so we're going to have 2 unknowns with a and b, but we're going to have as many zeros that we can apply. Okay, in this case, we're going to have 3 to eliminate b, and negative 2 so as to eliminate a, and setting s to 3. And we have 5 is equal to 5a, from which a is equal to 1. And if I set s to negative 2, okay, so a is going to go out, and for b, the coefficient is negative 5, and 3 times negative 2 minus 4 is negative 6 minus 4 shall be negative 10, and dividing negative 10 by negative 5, we have b to come out to 2. So we have a at 1 and b at 2. And so for the partial fraction decomposition, okay, I have, in this case, 1 over s minus 3 plus 2 over s plus 2. And putting back what we have in the setup for the integration over the inverse Laplace transform. So we have for the ratio, breaking it up, we have integrating over the inverse Laplace transform of 1 over s minus 3, and we have also plus 2 times the inverse Laplace transform of 1 over s plus 2, and again integrating over tau, and for the inverse Laplace transform of 1 over s minus 3, this would be e to the 3t, or in this case e to the 3 tau. And we have plus 2 times the inverse Laplace transform of 1 over s plus 2, which would be e to the negative 2t, or in this case we have e to the negative 2 tau. And taking the antiderivatives, and we're going to have what's going to be 1/3 of e to the 3t, and we're going to have, for the next term, we have what would be negative 1/2 of 2, which would be negative 1 of e to the negative 2 tau, as tau goes from 0 to t. And plugging in with the upper and lower limits, we're going to have 1/3 of e to the 3t, and we're going to have minus e to the negative 2t, and we have with the lower limits, we have minus 1/3 of e to the 0, which would be negative 1/3, and we have minus negative 1 times e to the 0, and that's going to translate to plus 1. So we will have constants to combine, whereupon we're going to end up with 1/3 of e to the 3t minus e to the negative 2t plus 2/3. All right, for the last problem, we have with f of s equal to 1 over s to the 4th minus 81, if I factor completely. Now we're going to have a sum of squares and a difference of squares, whereupon the difference of squares can be factored out to linear terms. So we have for the ratio, I have 1 all over s squared plus 9 quantity times the quantity of s plus 3 times that of s minus 3. And if I clear out the fractions, so I have 1 is equal to as plus b, okay, and each of as and b will be multiplied by both s plus 3 and s minus 3. And c will be multiplied by s squared plus 9 and s minus 3. And d is going to be multiplied by s squared plus 9 quantity and the quantity of s plus 3. And now we have 3 distinct zeros to choose from. From the s factor, I can choose 0. Since we have s plus 3, I can set s to negative 3. And from s minus 3, I can set s to 3. And we're out of real zeros that we can utilize. So in this case, I decided to arbitrarily choose s equal to 1. And plugging in 0, negative 3, positive 3, and positive 1. So I have these respective coefficients for the A, B, C, and D terms. And taking what we have and establishing a matrix, okay, where we have a 4x5 arrangement. Again, first column we have with the A term coefficients, second column the B term, third column the C terms, D column the D term coefficients, or fourth column the D term coefficients, and we have the last column. You have all the equations each set equal to 1. And applying what we have with the reduced row echelon form, it's going to turn out that A is negligible, B is equal to negative 1/18, C is equal to negative 1 over 108, and D we have at positive 1 over 108. And so with the breakdown here, we had the partial fraction decomposition laid out, and with the determination of f of t. Okay, so we have negative 1/18 of 1 over s squared plus 9. Now for 1 over s squared plus 9, now 9 is the square of k, and k is going to be at 3. And just rewriting, okay, the first set of terms. Okay, so negative 1/18 of 1 over s squared plus 9, that's going to be rewritten. Okay, so if I multiply the numerator 1 by 3, that means we had to multiply the denominator likewise. So I'm going to have in the rewrite negative 1/54 of the inverse Laplace transform of 3 over s squared plus 9, and that would result as a sine of 3t term. And I have minus 1 over 108 times the inverse Laplace transform of 1 over s plus 3. So for 1 over s plus 3, the inverse Laplace transform is going to be e to the negative 3t. And we have plus 1 over 108 times the inverse Laplace transform of the reciprocal of s minus 3. And the reciprocal of s minus 3 is going to have an inverse Laplace transform at e to the 3t. Okay, and so we have in the final result for f of t, we come out to negative 1/54 of the sine of 3t minus 1 over 108 times e to the negative 3t, and we have plus 1 over 108 times e to the 3t.